Hello everyone, I'm Yuanzheng Ci. This is the presentation for our ECCV paper, titled Fast-MoCo Boost Momentum-based Contrastive Learning with Combinatorial Patches. Contrastive-based self-supervised learning has achieved great success in recent years. It learns useful features by encouraging the encoded representation to be right to pretext transformations. And momentum-based contrastive learning significantly improved the self-supervised learning results by utilizing a momentum-updated teacher network to generate the contrastive target. But it only has one backwardable sample per 2 image forwarding. In this work, we propose Fast-MoCo, a method that generates more backwardable distinct samples nearly for free, with minimal modification to the original momentum-based contrastive learning pipeline, and significantly accelerates the training with negligible actual cost. In short, we additionally divide the input image into patches and recombine a subset of the encoded patch embeddings multiple times with replacement. The usage of these combinatorial patches resembles the bootstrapping technique in machine learning, where you draw a subset of dataset repeatedly with replacement. Here, we give a detailed illustration on how the combinatorial patches works. First, we simply divide the full resolution input image into multiple non-overlapping patches. Then, we treat the patches as distinct samples and encode them separately to retrieve the embedding for each patch. With all patch embeddings at hand, we draw a subset of them with replacement multiple times. In our experiments, the amount of embeddings belongs to the same image is usually small, 4 specifically in the default setting. We simply take all possible n combinations of those embeddings and average them, where n equals 2 in the displayed case. These representations retrieved by combinations are used as the actual samples for contrastive learning. Then, we update the online branch network with averaged gradient from all contrastive pairs, and a momentum update for the network on the target branch. This is the overall pipeline for the proposed method. For ImageNet linear evaluation result, our Fast-MoCo, which is basically MoCo v3 with combinatorial patches, when compared to the 800 epochs MoCo v3 baseline, has achieved a competitive performance with only 100 epochs of pre-training, which is approximately 7 times less training time considering the overhead of the additional operations, and 8 times less epochs in total. We also outperformed that baseline by a considerable margin with only 200 epochs of pre-training. And overall, we can achieve the same level of performance with much less epochs when compared to the other methods. The same is for downstream tasks like self-supervised learning, detection, and segmentation. The proposed combinatorial patches also works on other frameworks, such as methods with neighborhood-replaced target embedding, like NCLR, and non-contrastive methods like BIOL, and momentum-free methods like SimSim. It's worth noting that SimSim with our combinatorial patches achieves 71.7 accuracy with only 100 epochs of training, which is higher than SimSim's 800 epochs result. The proposed simple divide encode combine pipeline is only one way to implement the combinatorial patches. We also investigated many potential alternatives, and it turned out that the simple divide encode combine pipeline works best compared to those alternatives. Here is the ablation study of the patch size, which is determined by divide base number m and the number of combined patch embeddings per sample n. So n divided by m squared represents the portion of original image information contained within each combined embedding. You find choosing 2 times 2 split with n equals 2 have a good trade-off for all factors affected by these hyperparameters. That's all about this paper. Please check out our QR code for the open source code and pre-trained weights for this project. Thank you for listening.